Alright, in this lesson we're going to be learning about atoms, what they are, how to find them in the periodic table, and how to read the periodic table. It's all going to be very elementary and basic information. Okay, so when most people think about atoms, they think of something along the lines of this. Or this. I mean, that's not entirely wrong, but it's not entirely right either. But for now, I'll be using this just to explain what an atom is until we get a basic understanding, and in further videos I will debunk that and this. Alright. So, what exactly is an atom? An atom is what stuff is made of. So let's say you've got the graphite of your pencil. So graphite is made of carbon. Carbon is made of protons, neutrons, and electrons. And I'll get into this a bit later, but just know it's made of that. Okay? So a carbon is the smallest, a carbon atom is the smallest unit of matter that still retains the properties of carbon. You can't say, oh, we've got a carbon proton. No. Protons are protons, no matter what element. No, that there's no such thing as a carbon proton. Alright? But there is a carbon atom. You can say, hey, this is a carbon atom. Yes, that's completely correct. You can say, this is a carbon atom. Yeah, you can say that. But you can't say this is a carbon electron. No. Atoms are, again, the smallest unit of matter that still retains the properties of the original element, the original matter. Protons, neutrons, and electrons are all the same throughout the element, whether it's a carbon proton, well, you can't really say carbon proton, but whether it's a proton in carbon or a proton in radon, they're all the same exact thing. So, how do we figure out what is in carbon, how many protons it has, how many electrons it has, how many neutrons it has, and what exactly is all that stuff? Well, introducing the periodic table, and the periodic table essentially tells us information about each element, all 118 that we've discovered. Each little of these cubes is an element. Let's just talk about a hydrogen element. For now, it's quite simple. This is hydrogen. And that block of hydrogen tells us a lot of information. For example, it tells us the symbol. This is the symbol. It tells us the element name, which is hydrogen. So this is the name. And it tells us the atomic mass, which is 1.008 AMU. This is the atomic mass. And it also tells us the atomic number, which is always a whole number. It doesn't have units. And it's 1 for hydrogen in this case. And it tells us, and it's called the atomic number. Alright. So, what exactly is the atomic number and atomic mass? Well, atomic number tells us the number of protons. The atomic mass tells us the number of protons and neutrons. And I think right now is a perfect time to say that this is an average. Okay, don't confuse this with mass number, and I'll get into that a bit later, but this is an average number of protons and neutrons. So what exactly are protons and neutrons? Well, let's just say here's our hydrogen atom. Okay? Well, let's just say that blue represents protons, red represents neutrons, green represents electrons. Well, protons have a positive charge. They're just a particle with a positive charge. Neutrons have a neutral charge. Their charge is essentially 0. And that small little green dot is an electron, and they have a negative charge. So protons are about 1 AMU, roughly, not exactly. Electrons are roughly 0. Let me maintain the color coding here. Electrons are roughly 0 AMU, and neutrons are roughly 1 AMU. And this makes sense because these contribute the most to the mass of an element. That's why atomic mass is measured in protons and neutrons, because electrons really don't count much for the mass of an element, so that's why they're not considered in the atomic mass. For example, if you're still confused, let's just say you've got watermelon. Well, those seeds in the watermelon, they don't really count much for the mass of the watermelon itself. It's just mostly the watermelon stuff, and that watermelon stuff is the protons and the neutrons. So that's why electrons aren't really considered into that atomic mass. And I was going to talk a little bit more about this average part right here. Well, it's important to say that it's an average because the number of protons and neutrons is actually called the mass number. And I'll write that right here. The mass number is not shown on the periodic table, but some teachers allow you to just round this. So like you would round this to 1, or if it was 5.9, you'd round that to 6. But the mass number is the number of protons and neutrons. It's the exact number of protons and neutrons. So for example, this particular isotope of hydrogen, and I'll talk shortly about what an isotope is, has a mass number of 2 AMU, because 1 AMU plus 1 AMU is 2 AMU. And again, we're not counting the electrons because they're roughly 0 AMU, and that's not really important. And like I was saying earlier, this is an isotope of hydrogen. So isotopes are just different versions of an element with a different number of neutrons. So there could be an isotope of hydrogen with 2 neutrons, 3 neutrons, 4 neutrons. I mean, there's probably not any of those discovered recently, but it's possible. Isotopes are just different number of neutrons. And that's why this is an average, because this is the average number of isotopes. So it's the average mass of the isotopes. It's the average mass number of those isotopes. So that's why this particular hydrogen that I drew has 2 AMU, but the mass is still closer to, the atomic mass is still closer to 1, because most isotopes of hydrogen have only 1 AMU. Most of them are just 1 proton and 1 electron. There's no neutrons involved. So that's why this is an average, because most isotopes of hydrogen have just 1 proton, meaning their mass number is just 1 AMU, which leads to this being closer to 1 than it is to 2. Okay? So that makes sense? Alright. So now we know what protons, electrons, and neutrons all are. What role do they play in the element? Well, protons are what helps you identify the element. Please remember that. This is a very common test question. Protons are what identify the element. If you look at our little periodic table right here, it's not completely filled out, but let's just say that, well, actually, hydrogen has 1 proton, okay? And that little box right here is, this box right here is beryllium. Beryllium has 4 protons. This box up here is helium. Helium has 2 protons. Neon is right underneath, it has 10. And right to the left of neon is fluorine. It has 9 protons. So protons are what identify an element. There could be two neutrons here. There could also be 2 neutrons here. There could be 2 neutrons here, 2 neutrons here, 2 neutrons here. But there can never, ever be 9 protons here. There is no such thing as 9 protons of beryllium. If it has 9 protons, that means it's fluorine. It doesn't mean it's beryllium. So that's why protons are what identify the element. If you know it has 6 protons, you know it's carbon. 6 protons equals carbon. It will always equal carbon. There is no exceptions. Alright? Let me clean this up a bit. So that's the purpose of protons. They identify an element. Please remember that. It's extremely important. Alright, what's the purpose of an electron? Electrons are what bond atoms to each other and thus forms compounds. For example, H2O. We all know that as water. Well, H2O is just hydrogen bonded with oxygen. I mean, this isn't how it looks like. It more or less looks like this. But these little lines are bonds. They're not actual lines in there. It's just an attraction. Well, not an attraction, but it's the electrons sharing with each other, depending whether or not it's covalent or ionic. I'm not gonna get into that for now, but just know that this, just think of it as an attraction, but it's not an attraction. It's technically it's the sharing of electrons or taking away of electrons, depending if it's covalent or ionic. But electrons are, again, what bond atoms, and specifically the valence electrons. So, for example, let's say you've got this element right here. I don't know, I'm just making up these circles, but let's just say it has electrons here, electrons here. These electrons out here, these are called the valence electrons. Valence electrons are in the outermost shell. Okay, these little lines right here, these are called shells. These circles, they're shells, okay? These are shells or orbits. Do not call them orbitals. There's a difference between orbits and orbitals. These are orbits, not orbitals. Okay, so these are orbits. So on the outermost shell or orbit, they're called valence electrons. And valence electrons bond with other elements' valence electrons. And that's how they kind of like stick to each other, is from the electrons. They bond with other valence electrons of another atom. Okay, we're gonna get into compounds and ionic and covalent bonding in future videos, but for now, just know that electrons are what result in bonding, and specifically the valence electrons. These will be extremely important in future videos. Alright, so now let's move on to the neutrons. So neutrons really have no charge, and they're kind of just like the glue. So it might not be apparent in this diagram because it just has 1 proton, but let's just say we've got an element of, well, I was talking about beryllium earlier, so let's just say I've got an element of beryllium. So beryllium has 4 protons, let's just say it has 3 neutrons. So the neutrons are kind of the glue, because don't forget that opposites attract and like repel. And all these protons are all positive, and they all want to be away from each other. So the neutrons kind of force them together. It kind of glues them into a very dense area. And again, that area is the nucleus. So that's kind of the purpose of neutrons. It kind of like forces them together. It's like that one best friend who forces everyone who hates each other into just a new friendship or whatnot. So that's exactly what neutrons are. They think of these as enemies. They all want to get away from each other. But neutron is like a nice friend that keeps them all together. Neutrons are also what accommodate most of the mass, well, not most, accommodates the rest of the mass of an atom, because electrons don't have any mass, and let's say a carbon atom, for example, has just 6. A carbon atom has 6 protons, but its mass is roughly 12 AMU, so those 6 neutrons are what make it 12 AMU, because don't forget each one of these are 1 AMU, 1 AMU, so the neutrons are what result in that leftover weight and that leftover mass. Okay, so to wrap up this video, I'm going to start talking about the periodic table and the parts of it. Okay, so this area right here, this is the last column. These are called, well, that's not how I want that to turn out. These are called the noble gases. Okay. And then the first column is the alkaline metals. And there's a reason I didn't include hydrogen. Please do not include hydrogen. This is where a lot of students trip up. Hydrogen is not a metal. It's a non-metal. They only put it here because they just don't know where to put it. Hydrogen is kind of like an outsider. So again, this is called the alkaline earth metals. Alkaline earth metals. Okay. And then right here is the sorry, I mixed these up. This is actually the alkaline earth metals. This is not alkaline earth metals. These are just the alkali metals. Do not be like me. Do not mess these up on a test. These are alkali metals. I am very sorry for messing these up. These are alkali metals, okay? These are the alkaline earth metals. Let me just reinstate that. This is the alkali metals. This is the alkaline earth metals. Okay, got that. The first column is the alkali metals. The second column is the alkaline earth metals. Okay, and here there's lovely space in the middle. You don't really need to know anything about this space for now. It's a bit too complicated to try to understand, but this space right here is called transition metals. Okay. So after the transition metals, you get into the metalloids and the halogens. So the metalloids kind of go in a zigzag like this. Most people think of them as a staircase. So they go in a kind of like staircase motion right here. And these are metalloids because they're like metals and they're like non-metals. I haven't gone to the metals and non-metals yet, but I'll get into them very soon. Just know that these right here, they're called the metalloids. and they're like metals and like non-metals. Okay. So after the metalloids, you've got, well, I've already used that color. I'll just use white. So after the metalloids, you've got the halogens. And this is mostly what teachers need you to know. These are the halogens. And you've got your lactanides and anthonides near the bottom. Like right here is the actinides. Right here is the lanthanides. You don't really need to know what those are. Just some teachers like you to know them, but it's not required. So what exactly are these groups? So the alkali metals, they're basically organized on the number of valence electrons they have. Again, I told you, valence electrons are going to be very important, and starting now, they are. Okay. So alkali metals, they just have one valence electron. These alkaline earth metals have two valence electrons. These are kind of undecided. That's why they're just called transition metals. There is a way to figure that out, but I'll get into that later. But if you're just in middle school or early chemistry, you don't need to know how to figure those out. Metalloids, these are more or less organized on the fact that they're not metals, not non-metals. They're not organized on the number of valence electrons. They're just in between metals and non-metals. And they also divide the metals from non-metals. Like over here, this entire area, right to the left of them, well, to the left of them, not right to the left of them, to the left of them are metals, not including hydrogen. Hydrogen is a non-metal. It is very important that you know hydrogen is a non-metal. Just because it's over here, this is the only exception. Just because it's over here doesn't mean it's a metal. It's the only exception to this rule. Hydrogen is a non-metal. Okay. And to the right of the metalloids are your non-metals. Okay. To the left are the metals except hydrogen. Hydrogen is a non-metal. And to the right of the staircase are the non-metals. Okay. And the halogens have 7 valence electrons. And the noble gases have 8 valence electrons. They're called noble because they've got a full octet. And essentially what a full octet means is, there's some exceptions to this rule, but in general, all atoms want 8 electrons in their valence shell. And this is 8 valence electrons, so meaning they're happy, they're content, they're noble gases, they don't like to bond. They can bond to put in extreme circumstances, but they won't. This 7 valence electrons, they're very, very prone to bonding because they just need that one more valence electron to be happy, so the halogens really like to bond. As well as the alkaline metals, they also love to bond because they just need to lose that one valence electron to be happy. Because once they lose that one valence electron, they have other shells. Like, for example, this is hard to imagine. Let's say you've got this element. I'm just making this up. So let's say it has, it's 8 right here. 1, 2, 3, 4, 5, 6, 7, 8, and that has 2 right here. Let me draw these in a different color. So it has 2, 8, 1. Okay. Atoms are happy when they have a 2, 8, 8. There's exceptions to this rule, but typically atoms want 2 in the first shell, 8 in the second, 8 in the third. This has 1 in the third. So if it can just get rid of this pesky 1, it will be happy. It will have an 8 in its valence shell because now This will be its valence shell. This will be its valence shell. And now we'll have 8 electrons in its valence shell. Same thing with this, with the halogens. So let's just say you've got an atom right here. It has 2, 8, 7, 2, 4, 6, 7. It needs just one more to have a 288. So that's why it's really prone to bonding. And typically the halogens and the alkali metals like to bond with each other because that one extra valence electron it has can bond with that 7, and then they'll both have 8. But I'll get into the bonding a bit later. And if you're curious on how to know the valence electrons of like these over here, there's actually a way to read that on the periodic table. There's exceptions to this, but typically it's how it works. So you've probably seen, this is getting a little messy and I apologize, you've probably seen numbers on top of here. So those numbers are the number of valence electrons. You can read them that way. So you've probably seen 1, 2, 3, 4, 5, and then it goes all the way up to 12 over here. And then it goes into 13, 14, 15, 16, 17, 18 is all the way up here. For me, my personal trick is, again, these are all just question marks. I ignore these. You cannot, for the transition metals, you can't really know their valence electrons unless you want to do electron configurations, but I'll get into that a bit later. So I just like to read the last digit of these. So, and that tells me their valence electrons. So, for example, anything in here. This is, by the way, this is called a group. So anything in the first, groups go down. So anything in the first group has 1 valence electron. Anything in the second group has 2. Again, ignore the transition metals. Those are complicated. Anything in the 13th group has 3 valence electrons. Anything in the 14th group has 4. Anything in the 15th group has 5. Anything in the 16th group has 6. 17th group has 7. 18th group has 8. And in case you're curious, periods, they go this way. Okay, their periods don't tell you much about atoms. They're just called periods because they go horizontally. Anything in the same group have the same similar properties because they have the same valence electrons, and valence electrons determine the properties of atoms. You know, protons determine the identity of the atom, but valence electrons kind of determine their characteristics and whether or not they want to bond, how much they like to bond, and whatnot. Periods don't really tell you much. They tell you the how many shells there are, like the first period, the second period. First period has 1 shell, second period has 2 shells, and whatnot. But it's the groups are very important. It's very important that you know what the groups are because they tell you a lot about the elements and how they behave. And again, let me reiterate this. It's a very popular test question. Elements in the same group have the same properties. Like, for example, let's go to 13th group. Change stuff up a bit. 13th group has boron. Excuse me. 13th group has boron. And it also has gallium. Okay. Gallium and boron have very similar properties because they have the same number of valence electrons. But for example, 15th group has nitrogen. Borium and nitrogen, even though they're in the same period, that only means they have the same number of shells, or same number of shells or orbits, not the same number, again, same number of shells or orbits, not the same number of valence electrons. And valence electrons are very important. So just because boron and nitrogen are in the same period, it doesn't mean they share any really similar properties. The ones in the same group, like boron and gallium, are what share similar properties. If the question was nitrogen and arsenic, yes, those do share similar properties because they both have 5 valence electrons. So that's the end of this video, and it got a bit complicated and a bit messy, but main takeaway: atoms are made of protons, neutrons, electrons. Periodic table tells you a lot about atoms, where to find them, how many valence electrons, and valence electrons are what valence electrons are what determines the bonding properties and the characteristics of the atoms, and protons are what identify the atom. Okay? I hope this video was helpful, and if you did find it useful, please subscribe and like.